So one well-documented effect of selective attention on neural processing is to boost the signal for information that's currently attended compared to when it is not attended. So here we're looking at a cell that is tuned, that prefers a stimulus with that kind of orientation, so a bar with that kind of orientation. And you can see that even when the information is unattended, activity in that cell goes up as it notices the bar becoming closer to its preferred orientation. But with attention, so when the stimulus is also attended, that activity becomes significantly increased in terms of magnitude. And if you plot these activity levels in a graph like this, you'll see that even without attention, the cell will respond to its preferred stimulus, but with attention, that signal is boosted. So attention, so one effect of attention may be to boost activity when information is attended compared to when it is not attended. Now Moran and Desimone discovered an alternative role of attention on neural processing, which they did by doing monkey research and measuring the activity level in single units, so in single cells in visual cortex. And they presented the cell on each trial with two stimuli. One stimulus was the effective or the preferred stimulus for that cell, so the stimulus that the cell would normally respond to. Another stimulus was a non-preferred and ineffective stimulus for that cell. And there were two conditions: one condition in which the monkey attended to the preferred stimulus, and one condition in which the monkey attended to the unpreferred stimulus. And in this condition, the prediction and the finding was that attention would boost the activity level compared to baseline. So a baseline condition would be if these two stimuli were present but attention was directed somewhere else. And what would happen when attention goes to the preferred stimulus is that the activity in that cell would go up. And the question was what would happen in this situation when the cell still realized that its preferred stimulus is present because it is presented within the receptive field of that cell, but the monkey is not allowed to attend to it, it should attend to something else. What happens to the activity level of the cell in that case? And you may predict that one possible outcome is that without attention, the cell keeps its activity level exactly as baseline. So attention would have the effect on the activity of the cell of in a way switching it off, so not making it respond to the presence of its preferred stimulus at all. That would be quite a strong prediction. What Moran and Desimone found is that the effect is actually even more extreme than that, which is that the cell can reduce its activity compared to baseline if the preferred stimulus for the cell is present but not attended. So here we have a graph where it's plotted the proportion of the proportion of cells, the percentage of cells that reduce. Here we have plotted different proportions. So here we have plotted proportions of cells as a function of whether they keep their activity level exactly the same as baseline when the preferred stimulus for that cell is present but not attended, and that would be cells that are right on the line here. The cells that are to the right of the line would be cells that are more active without attention compared to baseline, so that when in this condition activity in the cell might go up, which you might predict because you might say, well, the preferred stimulus for the cell is present here, so even though there might not be a big effect, but the cell might still become a little bit more active compared to baseline. Whereas what Moran and Desimone found is that most cells would reduce their activity level compared to baseline. So activity levels would actually be pushed down by attention compared to baseline. So that's completely the opposite effect of what attention has when you attend to something. So a cell will increase its activity level when its preferred stimulus is attended, but that same cell will reduce its activity level when its preferred stimulus is present but not attended. And you can see that that doesn't happen when you present the two stimuli in different receptor fields. So one stimulus inside the receptor field of the cell and one outside, so you may have exactly the same visual setup, but if you make it so that only one of them falls within the receptor field of the cell, now you find that most cells will leave their activity level exactly as baseline, so they don't have this suppressing effect on the activity level of the cell. So that was quite strong evidence that attention can have this suppressing effect on neural processing. So Moyle and Desimone showed that attention can suppress processing of unattended stimuli, and we also know from behavioral studies that this may be the case, that attention can have this suppressing effect on ignored stimuli. And I want to show you two examples of this effect. One is negative priming and the other one is inhibition of return. In negative priming, the finding is that a previously ignored stimulus is slower or less easy to process when it has to be subsequently attended. So for example, if you look at this example here, and if the instruction here would be to attend to the black word and ignore the white word, so people here say car, and then on the next trial, and that's the important trial, sometimes this is called the prime trial, on the probe trial, people either have to respond to the word that they've just ignored, so they have to respond to the word dog here, compared to a word that they haven't seen at all, so the word pen. The typical finding is that it is a bit harder to respond to this word that has previously been seen but ignored, compared to a word that hasn't been seen at all, and you might get a difference of about 50 milliseconds, and people will also be a bit less accurate at that trial compared to a neutral baseline trial. So Tipper, who first reported this effect, used stimuli like this initially, so people had to respond to the red picture and ignore the green picture. So here you'd have to say chair and ignore the dog, and here you'd have to say dog and ignore the foot, and people would be relatively slow in this condition because they just ignored the dog picture and had to reactivate it now. They had to attend to it on the subsequent trial. So these are the typical trial conditions that you might have in a negative priming task. So given that your probe display might consist of a dog that needs to be attended to, so you need to say the word dog here, or you need to press a key to identify the dog and ignore the foot. If this stimulus was preceded by two completely different stimuli, that's a control condition, so your table concept gets activated here, your guitar concept gets suppressed, but none of those is repeated on the probe, so there's no effect of what happened previously. In an attended repetition condition, you attend to the dog and you ignore the spanner, you attend to the dog again on the probe, so that will speed you up. So compared to the baseline condition, this condition, having just seen the attended repetition condition, will make you a bit faster. But importantly, having just seen the ignored repetition condition, so having ignored the dog and attended to the trumpet, will make you a bit slower, again, compared to baseline. And how Tipper explained this effect is by saying that, so when you see your prime, so the first stimulus, what happens is that you activate your representation for the attended stimulus, in this case, let's look at the ignored repetition condition, in this case the trumpet, and at the same time you suppress your activation level for the ignored stimulus, so the dog, and that's because you need to try and minimize the potential conflict that you get from the dog here. So what you need to do is attend to the trumpet, you need to visually process it, you need to respond to it, so it's important that you go for the features that belong to the trumpet and ignore any features that belong to the dog, so you suppress anything that goes with the dog, and that inhibition, that suppression lingers, it doesn't go on and off immediately, but once you've suppressed it, that will linger for a little while, and it will still be below baseline by the time your probe comes along, and that means that when your probe comes along and your representation level for the previously unattended stimulus is still below baseline, will make you slightly slower and slightly less accurate to get that back up to your attended level. The other example of an inhibitory process in selective attention is inhibition of return, And inhibition of return is the finding that in visual search it's often more difficult to detect a target in a location that has been inspected previously compared to a location that was not previously attended at all. So if you're doing a visual search task, so you're looking for a target amongst a set of non-targets, once you've inspected one non-target location, you're less likely to go back to it, and that seems to make sense because a system that's reluctant to revisit previously attended locations will be more efficient. It will be less likely that you go back to somewhere where you've been already but you didn't find anything. And in the lab you can show this very easily by giving people a Posner style attention task, which we've seen in a previous class. So in the Posner paradigm, what you do is you measure how fast people can respond to a target item that can be either on the left or on the right of fixation, as a function of whether you've cued attention to that location or not. So in the Posner task it goes like this. So you, for example, light up, or you present a box here briefly which will cue people's attention towards it. So their attention, if I flash this up, your attention will go there automatically. It will stay there, and if the X comes up you'll be a bit quicker compared to if I cue this location and put the X over there, or vice versa. Inhibition of return is achieved by simply introducing an additional display in between the cue and the target, in which you ask people to move their attention back to its original position. So people start here, they are cued towards that location, but then nothing happens and they are asked to go back to the original location, and then you put the target in the location that you've previously cued. So in terms of attention, the idea is that this happens, so you go to that location, you go back to the center, but then if your target happens at that location that you've just been to, you'll be worse at picking it up, so you're a bit slower and a bit less accurate. And that suggests that what your system says is, I've been there, I didn't find anything, and I now think that something interesting is going to happen over there. And in terms of visual search, that seems an efficient way of keeping track of what's been visited, what's been inspected before. But what it suggests is that what we do in terms of how we guide our attention through our visual field is we keep track of where we've been before, and we kind of put some kind of inhibitory tag on the locations that have been inspected but have been unsuccessful in finding anything. So often inhibition of return is explained in terms of this kind of inhibitory process. So both these are examples that there may be a suppressive component in attention which dampens the processing of certain information. Together with the finding that attention can also increase activation for attended information, it suggests that those two mechanisms together, so both increasing in activation for attended information and reducing activation for unattended information, makes the net difference between what's attended and what's unattended greater, and that means that attended information stands out more. It kind of is more obvious in terms of its neural activity.